All right, so let's do this little warm up here. For theta between 0 inclusive and 2 pi non-inclusive, solve. We want sine of theta to be equal to negative square root of 3 over 2. So that means that there's how many solutions here based upon our unit circle knowledge? There's 2. What's the first angle where sine is negative square root of 3 halves? 4 pi thirds. Good. That's quadrant 3. That's going to be over here. And then where's the next one? Yeah, quadrant 4, 5 pi thirds. Okay, there you go. There's your answer. That's using the unit circle in reverse. Would you agree? Using the unit circle in reverse. Now, I've already taught you how we could actually solve that. Instead of just saying sine of what angle is negative square root of 3 over 2, we could take the inverse sine of both sides and we get theta equals inverse sine of negative square root of 3 over 2. And if we were in degree mode instead of radian mode, your calculator would give you 240 and 300 degrees, respectively. Okay? Because it doesn't do with the decimals for pi very well. But we could get the rate equivalent. So this is called what? This is called what? Inverse sine. It's called inverse sine. Okay? And notice that we take the inverse sine of a ratio to find a what? An angle. We take the inverse sine of a ratio to find an angle. Well, that's a perfect segue into what we're doing today, because chapter 5.7 is inverse trig functions. Now, notice we're saying inverse trig, what? Functions. What do you know about a function based upon its input? How many outputs are we allowed to have for a function per input? One, right? Max of one output per input. There doesn't have to be an output, but if there is an output, there can be no more than one. That means it has to pass the vertical line test. Well, what we just did over here, we got two solutions, didn't we? We got theta equals 4 pi thirds and 5 pi thirds. So there's going to be kind of an inherent little problem that we need to fix. When we talk about inverse sine, we need to agree upon which answer we want to accept as the answer for the function. Okay, so there's going to be a difference between inverse sine, the operation. Let me go ahead and write that right here. This is inverse sine, the operation. Like when we do add, subtract, multiply, divide, those are called operations. That's inverse sine, the operation. We do that to find however many angles that are in our given territory, in this case from 0 to 2 pi. But when we talk about inverse sine, the function, there could be only one output. And I'm wondering if it's going to be either one of these. If you had to choose one of those as the output to go with, what would you choose? Why 4 pi thirds? It's cooler. I agree. 4 pi thirds is cooler than 5 pi thirds. I would probably go with 5 pi thirds myself, just because I'm not as cool. I'm not as cool. But I would choose 5 pi thirds simply because the terminal ray is closer to 0. You see that? See how it's closer to 0? 4 pi thirds is like in a foreign land. It's way over there in quadrant 3. Man, it takes forever to get to quadrant 3, doesn't it? But if I can get to 5 pi thirds to that terminal ray, maybe I can get there by going what? Instead of going all the way around to it, maybe I can get there by going straight down to it. What would that angle be right there if I looked at it from negative 2 pi to 0? Negative pi thirds. Thank you, Brady. Man, I'm glad I went to the baseball game for you the other night. You're a smart kid. I don't want to stand with a freak-out dummy. Did you get into play? I didn't stay for the whole game. You didn't? Okay. Negative pi thirds. What do we call 5 pi thirds and negative pi thirds? They're what with each other? Coterminal with each other. Yeah, they're coterminal with each other. So let's go ahead and look at what an inverse trig function is by looking at first what a trig function is. All right. When I say f of x equals sine of x, the input is the angle. This is the input. And the sine ratio itself is the output. Would you agree? And for each angle, there's no more than how many outputs for sine? There's only one output for sine. It's Sahala, okay? It passes the vertical line test. But when we do it in reverse, we're going to have to agree upon one answer. So let's do it with the calculator now. we're going to need the calculator for this one. So it's kind of like the warm-up, but we're looking at something that's not on the unit circle. So I'm going to go to my Minnesota calculator. I recommend you do the same so you don't have to stand up. Minnesota, Minnesota, the finest state other than Texas. Minnesota, Minnesota. Thank you for giving us this calculator.
What if you ever get a comment on one of your videos from Minnesota?
No, but I get, not from Minnesota, but I get comments on my videos like, where did you get that calculator? Like other teachers want to like use it. Yeah. Oh yeah. Yeah. Like I'm like, you have to donate to korpisworld.com. If you make a little donation, I'll let you know. No, I just say you got to ask the governor of Minnesota is what I say. Just ask the governor. Here's the governor of Minnesota's email. He'll tell you. He'll send you the right direction. No, I'm nice. I send him the link. Why not? All right. So I want to solve for theta, and now I'm between 0 and 360. So instead of 0 to 2 pi in radians, I'm in degrees. Well, what do I have to do to unsign something? What's the inverse operation of signing something? Second sign, which is called what?
Sine inverse.
Yeah, sine inverse, or let's say it the other way around. Inverse sine. We read that as inverse sine is how we read it. Inverse sine. We take the inverse sine of both sides, and of course on the left side, inverse sine of theta is just theta. We did that earlier in the semester, or last semester, and we get inverse sine of 5/7. Now, this is where we need the calculator. Is 5/7 one of our unit circle ratios?
No.
It's not. What quadrants is it going to be in? Let's at least figure out the quadrants. Where is sine positive? Quadrant 1 and quadrant 2. Sine y, sine y. So sine is positive and y is positive. So I know it's going to be something between 0 and 90. There's theta 1. And then it's going to be something over here. We'll call this one theta 2 and quadrant 2. Now, all we got to do is go to our calculator. Go to mode. Go down to degree mode because it's default in radians. Switch to degree mode under mode. Then go second mode, quit. And now we'll just hit second sine of 5 divided by 7. Second sine of 5 divided by 7. And we get theta equals 45.584 degrees. Which angle is that? Is that theta 1 or theta 2? That's theta 1. All right, so to get theta 2, let's just type it in again. And this time we'll tell the calculator, give me the other answer, please. And then we hit enter. Crap, and it gave me the same answer. Let's try it again. Second enter. Abracadabra, calculator. Pretty please give me the other answer in quadrant 2. Enter. Crap. You know why the calculator is only giving us one answer every time? Go back to your mode. Look right below radian degree. What mode are we in? We're in function mode. The calculator knows to give us how many outputs? 1. It's only going to give us one output. So when we're doing inverse sine the operation to find all the solutions between 0 and 360, whose job is it to take the one answer the calculator gives us to find the others? Whose job is it? It's ours. Yeah. So how do we do that? We did this earlier last semester. This angle here and this angle here are both the same, aren't they? They're the same reference angle. So using my diagram, what do I have to do with 45.584 to find the other angle? Subtract it from 180, right? I got to stop that much short. So I'm going to do 180 minus second negative. That recalls the answer. And I get 134.415, and I round or truncate to 3 decimals degrees. Now, let's check that one. If I hit sine of second answer, I get this number here, which when I hit math enter converts back to what? 5/7. So there's only one sine value for 134, but to have a sine value of the same one that sine of 134 does, which is 5/7, there's infinitely many angles. So what we're going to learn in this section is basically how do we decide on which single answer, when we're talking about the function, how do we decide on which single answer we're going to use? Okay, the calculator knows which answer to give you. When your calculator was programmed as a function mode calculator, it was programmed, hey, give one answer and one answer only. And it was told which answer to give you. So if we're talking about inverse sine the function, there's only one answer, 45.584. But if we want to know what are all the angles whose sine value is 5/7 between 0 and 360, now there's two answers, right? All right. Any questions so far? You getting the hang of it? So far, so good? So good so far. All right. Now, let's talk about inverse sine because we flipped the input and the output. When we're talking about inverse sine, the ratio is now the input. And the inverse sine itself is the angle, which is the output. So the inputs and outputs change. We take sine of angles to find ratios, but we take inverse sine of ratios to find what? Angles. Yeah. Yeah. So let's figure out how we're going to remedy the fact that there's only one solution and there's really infinitely many. How do we decide out of infinitely many which one? Well, it takes us to this little piece right here, which is called a one-to-one function. And I know we've seen this in algebra too. A one-to-one function is like a Minnie Mouse and Mickey Mouse, right? For every Mickey Mouse, there's how many Minnie Mice? There's only one. There's only one Minnie. Minnie has Mickey's heart, and vice versa. For every Minnie Mouse, how many Mickey Mouses are there? There's just one. Minnie Mouse and Mickey Mouse are a faithfully monogamous pair. Okay? That's what one-to-one means. That means for every x, there's only one y, which is the definition of a function, but it works the other way around too. For every y, there's only one x. Is sine a one-to-one function? For every angle, for every ratio, is there only one angle associated with it? No. Okay? You could tell a function is not one-to-one by looking at what's called the horizontal line test. Because a one-to-one function not only passes the vertical line test, it passes the horizontal line test. And sine of x fails the horizontal line test, doesn't it? Sahala fails the horizontal line test. Okay? X squared fails the horizontal line test. If I asked you what's the square root of 25, you would tell me 5 and -5, I hope, right? There's two outputs. That's not good. All right? So if we want to know that a function has only one output when we take its inverse, we have to make sure it's a one-to-one function. A one-to-one function has only one output per input and only one input per output. Okay. What happens then when we take the inverse? Well, the domain and range flip. Okay. The domain and range flip. So if f inverse of x equals y, then f of y equals x. In other words, you have the point xy on one function, and that means the point yx is a point on the other function. Okay. They are each other's inverses, and there's only one. There's only one y for x, and there's only one x for y. Got it? That's one-to-one. All right, let's look at sine of x then, and we'll see what we can do to make it one-to-one. We're going to have to agree on some things here. So quickly sketch Sahala. Give yourself a y-axis, give yourself an x-axis, and let's just put a couple of points on here. Here's 2 pi, here's pi halves, here's 3 pi halves. We'll graph 2 cycles from -2 pi, -pi, -pi halves, -3 pi halves. We're setting the table here, right? We go up to 1, we go down to -1, and then we do Sahala. Axis high, axis low, axis. And then we work backwards, low, axis high, axis. And then we connect them with nice little quarter cycle arcs. This we've done literally a million times, right? Maybe not literally a million times, but it's our parent function. This is f of x equals sine of x. Does it pass the vertical line test? Yeah, it passes the vertical line test. So for every angle, there's how many sine values? For any given angle, there's only how many sine values? One. There's only one. But for any given sine value, there's how many angles associated with it? Infinitely many. This fails the horizontal line test. Yes? Okay, so here's the trade-off. We have to find a one-to-one interval, and we got to restrict the domain. Remember in Algebra 2, you learned about restricting domains? We got to restrict the domain. And here's the thing. We got to restrict the domain to A, number one, convenient. Number two, one-to-one interval. And number three, that contains all the y values from -1 to 1. Whoa, that's kind of a big task, right? I want to find a convenient one-to-one interval that includes all of the y values from -1 to 1. If it doesn't include the entire range, then it's not worth looking at. Well, every half cycle, let's look at that. So let's start by just saying, would it work to look from 0 to pi? That's a half cycle, right? That's convenient, right? What makes this interval convenient? Well, convenient just means near 0. Let me add that here. Near the origin. This is definitely convenient. It's near the origin, right? It actually has 0 as its left bound. Okay, so it is convenient, but is that section 1 to 1? No, that section right there itself fails the horizontal line test. So we don't want to go from 0 to pi. The second thing not only fails, the third thing fails too. It doesn't contain all the y ratios from 0 to 1, does it? I mean, from -1 to 1. It only contains the ratio values from 0 to 1. So that's not going to work. But I think the half cycle thing is good. We want to look on a half cycle here. Negative pi halves to pi halves. Let's see if that works. Negative pi halves to pi halves. If I look on this interval here, let's see what we're talking about. You would include negative pi halves and pi halves, right? So we got -1, and then we're getting all of the y values between -1 and +1. So first of all, is that convenient? Is it near the origin? Yeah, it's actually closer to the origin than the other interval from 0 to pi. It only spans pi halves away, but on each side. Yes, yes? Okay, so it is convenient. Is that little purple interval 1 to 1? Does the purple graph part pass the horizontal line test by itself? Yes, yes. And does it thirdly include all the y values from -1 to 1? Yes. Okay, good. So that works. What about, since we have that idea, what about from -3 pi halves to pi halves? Would that be a 1 to 1 interval on that green interval? Would that be 1 to 1? It would be 1 to 1. Would it include all the values from -1 to 1? Yes, but is it as convenient? It's not as convenient. It's further away, right? It's further away. What about the interval from pi halves to 3 pi halves? Is that little gray section 1 to 1? Yes. Does it include all the values from -1 to 1? Yes, but is it as convenient? No. So the most convenient 1 to 1 interval that includes all the y values is going to be from negative pi halves to pi halves. And guess what? That is, y'all discovered it on your own based on the criteria. That is the interval that we restrict sine on. We restrict sine from negative pi halves to pi halves. If we then reflected that purple piece only across the line y equals x, okay? If you only reflect that piece across the line y equals x, let's think about what's going to happen. First of all, what happens to the x and y axis when you reflect something across the line y equals x? Remember that, if you remember from algebra 2, you reflect it across the line y equals x. This is your magical mirror. What happens to the point pi halves comma 1? It turns into 1 comma pi halves. Yep. And what happens to the point negative pi halves negative 1? -1 negative pi halves. Yeah. It looks like that. And then the rest of it, it's going to look like this. If you want to kind of think about what it might look like, I'll draw it in kind of red. It kind of reflects across itself like that and does that. So if you can imagine looking across that 45-degree line, it looks like the purple and the red would line up with each other if you fold it, doesn't it? So that's how I'm going to fill in over here. It still passes through the origin. 0, 0 is still 0, 0. But it looks like this, and it looks like that. And it stops. This is your graph of inverse sine of x. Now, to show that it's an inverse sine function, what I typically do is I use a capital letter. Okay? Capital letter. It doesn't need to be capitalized. If it says f of x equals, you know it's the function. But a lot of times I put the capital letter just to help it stand out a little bit more. But it doesn't need a capital letter. If it follows f of x, we know it's a function. All right, now, the other parts that we didn't graph, if you want to see what they would look like, it would snake back and forth left and right like this across the y-axis. That's what the rest of the piece of sine would look like. But we're not looking at those other pieces, are we? They're too far away from the origin. So that little red piece right there with little endpoints, as that little balls as endpoints, that's your graph of inverse sine. What's the domain of inverse sine? -1 to 1. And those represent what? Angles or ratios? Those are ratios. Yeah. And the range, which we also call the principal, it is the range, but sometimes we call it the principal value range. The principal value range, or just the PVR for short. What's the principal value range or the range? Negative pi halves to pi halves. Yeah. The reason we call it the principal value range, principal kind of means main, doesn't it? Or primary. There are other ranges we could have used, right? But we said they were too far away from the origin. So sometimes we make the distinction that, hey, there are other places where you could have restricted it, but these are the ones that are the most convenient. So these are the main ones. These are the principal ones. And we're going to agree to use answers only in that interval, okay? That's it. It's a monotonic increasing function. Does it still have origin symmetry?
Yeah.
Yeah, it has origin symmetry. That's kind of cool. It's still an odd function. But here's kind of what it does on the unit circle now. If I think about the unit circle, pi halves is up here, and negative pi halves is down here. So if I'm looking from 0 to pi halves, I'm going up into quadrant 1. But if I look down to negative pi halves, I'm going into quadrant 4. See that? So this is very, very interesting. If you take the inverse sine of a positive number, you're going to get a positive acute angle between 0 and 90 degrees. But if you take the inverse sine of a negative number, you're not going to get all the way into quadrant 4 by going all the way around past 270. You're going to get into quadrant 4 directly by going clockwise by an acute amount. Okay? So if you ever take the inverse sine of a negative number, you're going to get a negative acute angle. Let's try it out. If I hit inverse sine, I'm in degree mode still. If I hit inverse sine of square root of 2 over 2, what should I get if I take the inverse sine of the square root of 2 over 2? Remember, your calculator is programmed in function mode, so it's only going to give you one answer. What's the answer? 45 degrees, right? It's a positive acute angle, so it's going to give me it's going to give me a positive. I'm sorry, it's a positive ratio, so it's going to give me a positive acute angle in quadrant 1. But what if I take the inverse sine now of negative square root of 2 over 2? It's going to give me negative 45, not 315. See that? 315 is coterminal with it, and 315 is between 0 and 360, but that's not what the calculator is programmed to do. It gets to that angle by going down straight to it directly. So here's what's cool. When you take the inverse sine of a ratio, you always get an acute angle. Plus or minus. You always get plus or minus an acute angle. You're never going to get an obtuse angle when you take the inverse sine of something in function mode. It's always plus or minus an acute angle. Got it? Okay. So there you go. We all agreed on negative pi halves to pi halves, didn't we? We all agreed to that based upon the criteria. It was the most convenient one-to-one interval. Okay, so there you go. Now, there's another name that we give to the inverse sine function, and it's called the arc sine function. Here's why we have another distinction. Let's look at this. If I write sine squared of x, that means sine of x quantity squared. Yes, yes? The left side is the condensed, the right side is the expanded. They mean the exact same thing. You might think then that if I write sine to the negative first of x, that equals sine of x to the negative first, right? Well, sine of x to the negative first is 1 over sine of x, which is actually cosecant of x. Can inverse sine of x equal cosecant of x? There's absolutely no way, because inverse sine of x, we take it as a ratio input, and cosecant of x is an angle input. So where does it break down? It breaks down right there. So whenever you have a number that's written between the n and the x for sine of x, any other number except -1 means that it's raised to that power. Like if I put sine to the negative second there, that would mean sine of x to the negative second power. But if you see a -1 there, the -1 is reserved to be inverse sine. This is reserved for inverse sine. Now, because that's possibly inherently confusing, right? You're like, it looks the same. It's in the same spot. Why can't we do the same thing? Because it's reserved. Okay, we reserve. We were here first. We're saving these seats, buddy. Move on. We have another name for it. Okay, inverse sine of x now is also the same as arc sine of x. They mean the exact same thing. Arc sine of x. Okay, the reason that we use arc is because, remember, we're talking about finding a radian angle, which is a ratio of an arc length to the angle that subtends it, to the radius. Okay, the arc length is the radius. I'm sorry, the radian measure of an angle is the arc length divided by the radius. So that's why we use arc. It's related to the radian. So what's another name for inverse sine? Arc sine. What's another name for arc sine? Inverse sine. Now, having said that, I actually prefer using arc sine when I write things out because it is inherently confusing. But what is it on the calculator always? It's always inverse sine on the calculator. So just keep that in mind. If you see arc sine, that means inverse sine, and inverse sine means arc sine.
So are the other inverse functions just like arc, cosine?
They work the same way. Yeah, we'll get there. Arc cosine is the same as inverse cosine. Arc cosecant is the same as inverse cosecant. The same kind of terminology works for the other 5 trig functions. You're absolutely right. Okay. Let's try it out. If f of x is equal to inverse sine of x. Now notice the inverse sine of x there is not capitalized, is it? But is it the function with only one output? And the answer has to be in the PVR? Or is it the operation where I'm finding all the solutions in a given interval? How do you know it's the function, Brady? Well, how do you know it's a function right there? It says what? F of x. So that means we're looking for the function, which means this. It means one output only in the PVR. What does PVR stand for? Principal value range, which remember, the principal value range for arc sine is negative pi halves to pi halves. So you could think of it as a half moon. I like to think of it as the half moon. I sure did. There you go. If you take the inverse sine of a positive ratio, you're getting a positive acute angle. And if you take the inverse sine of a negative ratio, you're getting a negative acute angle. Half moon, all right? So arc sine or inverse sine is the half moon. Got it? Half moon. All right, let's try it out. What is f of 1/2? Well, that's the same thing as inverse sine of 1/2, which is really the same thing as arc sine of 1/2, which is the same question you ask yourself this. What is the angle in the PVR whose sine, I have an S there, whose sine is 1/2? In other words, where is sine equal to 1/2 in quadrant what? What quadrant are we going to be in? We're going to be in quadrant 1. What's the angle in quadrant 1 only where sine is 1/2? Are we in degrees or radians? Give your answer in radians. Pi thirds? Pi 6. We're using the unit circle in reverse. Let's try it going forward. What's sine of pi 6? 1/2. What's inverse sine of 1/2? Pi 6. What's sine of pi 6? 1/2. What's arc sine of 1/2? Pi 6. Now, let's do a follow-up question. What's sine of 5 pi 6? Sine of 5 pi 6 is still 1/2. So why is arc sine of 1/2 not 5 pi 6? It's in function mode, and 5 pi 6, just say 5 pi 6 is not in the what? It's not in the PVR. Thank you, Ryan. It's not in the PVR. It's not in the principal value range. So yeah, there's infinitely many angles whose sine is positive 1/2. Did you know that? They're all coterminal with pi 6 and 5 pi 6, but there's infinitely many of them. We only want the one that is positive in quadrant 1. Hey, welcome. All right, let's try letter B, f of negative 1/2. That's the same as arc sine of negative 1/2. If I think about the half moon, if I think about the arc sine half moon PVR for arc sine, it's positive in quadrant 1, it's negative when it's in quadrant 4. We have a negative ratio, don't we? So I want the negative acute angle. So what is it? Negative pi 6. Yeah, yeah. What's sine of negative pi 6? Negative 1/2. So what's arc sine of negative 1/2? Negative pi 6. Hey, what's sine of 11 pi 6? What's sine of 11 pi 6? Negative 1/2. So why isn't arc sine of negative 1/2 11 pi 6? 11 pi 6 is not in the PVR. It terminates at the same place though, doesn't it? Yeah, but 11 pi 6 gets there by going all the way around, and we don't want to do that. We want to get there by going straight to it. See that? They have the same sine value, but we're not getting there by rotating all the way around. We're going straight to it. You got it? You see what we're doing here? All right. Let's see if the calculator knows that. Second sine of negative 0.5. It should tell us that it's what if it's in degree mode? Pi 6 is how many degrees? 30, yeah. So it gives us negative 30. Is that right? Negative 30 in degree mode? Yeah, the calculator knows because it's programmed that way. I'm trying to program y'all now that way. All right? All right, sweet. What about f of negative square root of 3/2? This is the one that we started with in the warm-up. This is the same as arc sine of negative square root of 3/2. On the warm-up, we came up with these two answers. We came up with 4 pi thirds and 5 pi thirds. Which of those, if any, is going to be the answer now to the function arc sine of 5 pi thirds? Square root of 3/2. 5 pi thirds? Ugh. Is 5 pi thirds in the PVR? No, it's negative pi thirds. We're not going to get to that terminal array by going all the way around counterclockwise. No, we get to that spot directly and succinctly by going straight down clockwise to it, negative pi thirds. So the two answers from the warm-up, neither one of them make the cut. It's negative pi thirds. Negative pi thirds. See that? You got it? Are y'all being programmed properly? What's sine of 5 pi thirds? No. Negative square root of 3/2. Sine of 5 pi thirds is negative square root of 3/2. But what's the inverse sine of negative square root of 3/2? It's just negative pi thirds. We get there directly. Okay, cool. All right, f of 1 means inverse sine of 1, which also means arc sine of 1. So where is that going to live? Well, no, this is positive, this is negative, and remember, straight up is 0, 1, straight down is 0, negative 1. So what if we have inverse, and this is the point 1, 0. This is the point 1, 0 right here. So if you ever have inverse sine of 1, 0, or negative 1, it's going to be on one of the quadrantal angles, isn't it? Inverse sine of 1, what's the ordered pair straight up at 0, 1? Pi halves. So what's inverse sine of 1? Pi halves. What if it were inverse sine of 0? What angle is at 0? 0. And what if it were inverse sine of negative 1? What angle's down there? Good. Not 3 pi halves, negative pi halves. So if you land on one of those, 1, 0, or negative 1, you're going to get one of those quadrantal angles, pi halves 0 and negative pi halves respectively. Got it? Let's see if the calculator knows that. Second sine of 1, it should give us what as an answer in degree mode? Which is 90 degrees. Yeah. And it does, right? Let's do negative 1. What should it give us? Second sine of negative 1 should give us what? Negative 90. It does. The calculator is programmed. Let's do 0. Second sine of 0 should give us what? 0. It does. It's programmed like y'all now, right? All right, how about f of pi? That's inverse sine of pi or arc sine of pi. Same thing. What angle gives us a ratio of pi? What quadrant would it be in if it were in any quadrant? Quadrant 1 or 4? It's in quadrant 1 because it's positive, right? So what is the angle in quadrant 1 where the sine ratio is pi? Is pi an angle or a ratio in this context? No. It's a ratio, right? Pi is just a number. In this context, it's a ratio. How do I know it's a ratio and not an angle? We're trying to find the inverse, right? If it follows inverse or arc, it's a ratio. Yes, yes? If it follows an inverse or an arc, it's a ratio. So, what do we know about the sine ratio? It's y over r. We're trying to figure out where that's pi over 1. Is that even possible? To have a short leg called y that is pi times bigger than the hypotenuse radius of 1? You can't have a short leg bigger than the hypotenuse, can you? So what should the answer be? Is there a sine ratio of pi? It's dne. Yeah, if you think about the graph of sine, Sahala, it only goes up to 1 and down to negative 1, right? It doesn't go up to pi. Let's see if the calculator knows that. Second sine of pi. Error. Oh, go to value not allowed in the function. Error domain. Error domain. Go to. Can't take pi. All right. Calculator's programmed. Are y'all programmed? Y'all are programmed now. All right. Let's try it on the calculator exclusively. Example 4. If f of x is arc sine of x. Hey, what's another name for arc sine of x? Inverse sine of x. Are we talking about the operation where there's multiple answers or the function where there's only one? Function where there's only one. It's f of x. Okay, using a calculator, evaluate the following to 3 decimal places in radians. Okay, so now I got to be in radians. So what do I do in my calculator first? I go to mode, come down to radians, and I switch back. And now, how do I type in f of 0.82? That's the same as, yeah, even though it's arc sine, I hit second sine of 0.82. What quadrant is it going to be in if it's a positive ratio? Quadrant 1. I get 0.961 rads, which is quadrant 1. Yep. Cool.
On the quiz or something, do you want us to write down arc sine 0.82?
No, you don't have to.
Okay.
In fact, let's not do it on the next one. What's f of negative 1/3? What quadrant is it going to be in? It's going to be quadrant 4, right? So it's going to be a negative acute angle. Second sine of negative 1 divided by 3. Let's just write it down. Negative 0.339 or 340 rads. I put rads to remind us that it's an angle. Is that a negative acute angle? Yeah. Yeah, it looks good. All right, how about f of 3 halves? What quadrant is that going to be in? Are you sure? Oh, do we ever go into 2? Do we ever go into 3? No. It's either 1 or 4. Why DNE? What do we know about 3 halves in relation to 1? It's bigger. Can you have a sine ratio bigger than 1? Can you have a sine ratio smaller than -1? No, so it should be D and E. Second sine of 3 divided by 2, not in the function, okay? Your
Oh, never mind. Sorry.
3/2 is bigger than 1, right? You can't have a sine ratio bigger than 1 or a sine ratio smaller than 1. Okay, we'll stop right there. That's a good place to stop for today. We'll start with example 5 tomorrow, and then tomorrow we'll learn about inverse cosine and maybe even inverse tangent. Any questions? Memorize the unit circle half moon, all right? Quadrant 1, quadrant 4. Quadrant 1, quadrant 4. All right, we'd be done.